Hi, in this video we will look at how ammonia is made in the Haber-Bosch process, and we will look in detail using Le Chatelier's principle at the conditions which are used to make ammonia. Fertilisers play a crucial role in modern agriculture by replenishing essential nutrients in the soil and improving crop yields. Now, as the world population grows, the demand for food is increasing, and without the use of fertilisers, many people would simply go hungry. Now, many common fertilisers can be made from a compound called ammonia. Now, ammonia is a very simple molecule composed of 3 atoms of hydrogen, covalently bonded to an atom of nitrogen. At first glance, it would seem simple and straightforward to synthesize or produce such a small and simple molecule, but unfortunately, the synthesis of ammonia proved not so straightforward after all. Now, in this video, we will study the process developed by the German chemist Fritz Haber for making ammonia. Now, Haber was a scientist who in 1909 managed to synthesize ammonia using nitrogen gas from the air and hydrogen gas. Now, while Haber developed the process to produce ammonia, it was another German chemist and engineer called Karl Bosch who managed to scale up the process to enable large amounts of ammonia to be produced. Now, Fritz Haber made ammonia by reacting together the gases nitrogen and hydrogen. However, this reaction to make ammonia is a reversible one. This means that once started, the reaction mixture will be a mixture of reactants and products. Now, an equation for this reaction is shown on screen. Now, recall that reversible reactions will eventually reach equilibrium. That is, a position where the rate of the forward and the rate of the reverse reactions are equal. However, the amount of reactants and products present in an equilibrium mixture will depend entirely on the reacting conditions. And unfortunately for Haber, at room temperature and pressure, the amount of ammonia present in an equilibrium mixture is very small. In fact, it is only around 1% ammonia, with the remaining 99% being unreacted nitrogen and hydrogen gases. So one of the challenges for Haber was to alter the reacting conditions to ensure that a much larger yield of ammonia could be produced. Now, in any reversible reaction, such as the one used to make ammonia in the Haber process, it is possible to change the amount of reactants and products present by simply changing the reaction conditions, usually by changing the temperature, pressure, or concentration of one or more of the reactants or products. Now, Haber used the work and research of the French chemist Henri Le Chatelier to try and work out how to increase the amount of ammonia present in an equilibrium mixture of nitrogen, hydrogen and ammonia. Now, Henri Le Chatelier was a French industrial chemist who was best known for his work on chemical equilibrium and for Le Chatelier's principle. This principle states that a system, that is just simply the reacting chemicals, in an equilibrium mixture, which is subjected to change in reaction conditions, will shift in direction so that these changes are opposed or minimized. So let's use Le Chatelier's principle to work out how changing the temperature, pressure, and the use of a catalyst will change the amount of ammonia present in the Haber process. So let's start by looking at how an increase in temperature will affect the amount of ammonia present. Now, the forward reaction in the Haber process is exothermic. That is, it releases heat energy to the surroundings, while the back reaction, that is the decomposition of ammonia into nitrogen and hydrogen, is an endothermic process. So what would happen if we increase the temperature of this reaction mixture? Well, according to Le Chatelier's principle, the reacting chemicals or the system will try to oppose or minimize the increase in temperature. The only way to do this would be to increase the rate of the back reaction. That is the endothermic reaction, which, as you may recall, is a reaction that takes in heat energy from the surroundings. This means that the amount of ammonia present in the equilibrium mixture will decrease. This is the exact opposite of what we would like. So increasing the temperature will reduce the amount of ammonia present. So how about if we decrease the temperature? Well, this time the system will try to oppose the decrease in temperature, and so the rate of the forward exothermic reaction will increase. Now this looks promising, as this will increase the amount of ammonia present in the equilibrium mixture. However, there's a big problem here. You may remember that reducing the temperature will also slow down the rate of reaction. So ultimately, you may end up with more ammonia present in the equilibrium mixture, but it may take a very long time to get there. So what we need is a compromise temperature. That is one which is not too low that it will slow down the reaction so that it takes too long to produce any ammonia, and one that is not too high, that is, it will reduce the amount of ammonia present in the equilibrium mixture. So a compromise temperature of around 450 degrees Celsius is chosen. This might seem quite high, but it is not really when you consider that most chemical processes operate above or around 900 degrees Celsius. Now let's take a look at how altering the pressure can affect the yield of ammonia in the Haber process. Firstly, it is worth saying that pressure will only have an effect on a reversible reaction at equilibrium if there are gases present, and this won't be a problem since in the Haber process all the reactant and product molecules are indeed gases. Now from the equation shown for the Haber process, we can see that on the reactant side of the equation we have 4 moles of gas, that is 3 moles of hydrogen gas and 1 mole of nitrogen gas, while on the product side there are only 2 moles of ammonia gas present. We can imagine then that the product side of the equation can be considered as the low pressure side for the reaction, since it contains only 2 moles of gas, whereas the reactant side can be thought of as a high pressure side for this reaction, since it contains 4 moles of gas. So as before, we can use Le Chatelier's principle to work out what will happen when we change the pressure. Now if you change the pressure, then according to Le Chatelier, we will be applying a stress on the system and it will try to reduce or oppose this stress. So what will happen if we increase the pressure on the system or reacting molecules? Well, since there are fewer moles of gas on the product side of the reaction, that is, the low pressure side, then increasing the pressure favours the formation of ammonia. So increasing the pressure will lead to an increase in the rate of the forward reaction and a decrease in the rate of the back reaction. So overall, we can say that increasing the pressure will result in an increase in the production of ammonia. The opposite is true if we decrease the pressure. Here the system will try to increase the pressure by reducing the rate of the forward reaction and increasing the rate of the back reaction. This will of course lead to a reduction in the amount of ammonia produced. However, as with temperature, there is a compromise to be made here. High pressure is expensive, and any industrial process involving high pressure requires strong and expensive equipment. So while maximising pressure favours the production of ammonia, it also leads to an increase in costs. So a balance needs to be struck between the amount of ammonia produced and the cost of the chemical plant. A pressure of around 200 atmospheres is usually used, as this is a reasonable compromise between cost and the amount of ammonia produced. Now the final piece in the jigsaw for Haber was finding a suitable catalyst for the reaction. Now the forward reaction in making ammonia, that is the reaction between the nitrogen and hydrogen atoms, has a very large activation energy. This is mainly due to the presence of the triple covalent bond between the nitrogen atoms. Haber knew that he would have to use a catalyst to lower this activation energy so that the reaction would proceed at a reasonable rate. Now the catalyst needed to be readily available, it needed to be affordable for large-scale processes, it should be able to withstand the high pressure and the temperature used inside the reaction vessel, and it must be able to promote the desired reaction. After many experiments, Haber settled on the use of an activated ion catalyst. The animation on screen shows a simplified version of the Haber process in operation. Now, at the start of the process, the nitrogen and hydrogen gases are mixed in the ratio of 1 part nitrogen to 3 parts hydrogen. These gases are then preheated to around 450 degrees Celsius and compressed to a pressure of around 200 atmospheres. This mixture of gases then enters the reaction chamber containing the hot ion catalyst. The nitrogen and hydrogen gases then react on the surface of the catalyst to form ammonia. A typical yield here is around 15% ammonia, with 85% of the nitrogen and hydrogen not reacting. This mixture of ammonia and unreacted nitrogen and hydrogen gases then leaves the reaction vessel, and it enters a cooler where the ammonia liquefies before being removed. The unreacted nitrogen and hydrogen is then recycled back through the reactor again to form more ammonia. Hi, thanks for watching. If you found this video helpful or would simply like more information, then why not visit the website that accompanies these videos? The links are in the description below. If you enjoyed the video, then please consider liking and subscribing. Thank you.